Okay, so we are discussing different tracking loop discriminators. We talked about the pooling range. This is the range uh, where if the actual error lies, the discriminator output will have the correct sign, and with the help of negative feedback control, the loop can bring the error to 0. Okay. Now, over this pooling range, not the entire region is linear. Only a part of it here, in case of the DLL discriminator, the relationship between the actual error and the discriminator output is linearly related. And it is shown by this straight line here. Now the range over which the relationship is linear is determined by D. Okay. D is the early and late correlator spacing. We know that early is shifted ahead of the prompt by D by 2 chips and left is shifted behind the prompt. Here I don't have. Late is shifted behind the prompt by D by 2 chips. So the code phase offset between early and late is D. Now the standard value of D is 1 chip. Okay. It can be shown that for these discriminators, the ones that are shown here, the linear range is within plus minus D by 2. Since D is equal to 1 for this plot, it is plus minus 0.5. Okay. Now, while doing acquisition, the step size of the candidate values of CP is generally chosen as 0.5 chip. It can be lower than that also. So this means that the code phase error tau will be within 0.5 chips. So after acquisition, the error is expected to be in this region. And then with the help of negative feedback control, the loop will try to bring it to 0. Okay. Similarly, in case of the FLL discriminator, there is a pooling range, which is a function of the coherent integration time. Okay. So this solid line here shows the 8 and 2 discriminator, FLL discriminator. The corresponding function is shown here. Its pooling range is plus minus 50 Hz. And for this discriminator, the linear range and pooling range are the same. Whereas for ATAN, in place of ATAN 2, if you take 2 quadrant arctangent function, ATAN discriminator shown by this dashed line, the pooling range is half, plus minus 25 Hz. And again, the linear range is the same as the pooling range. The dotted line shows the cross product discriminator, whose function is given by this. We are considering 2 pairs of prompt correlators over 2 successive T coherent intervals. So each is formed over 10 milliseconds. In case of the cross product discriminator, this is the pooling range. Again, plus minus 50 Hz, but the linear range is this much only. So the cross product discriminator does not have the same linear range as the pooling range. Now, how the pooling range is determined by these discriminators? It is actually a function of the coherent integration time. Okay. For the 8 and 2 discriminator and also for the cross product discriminator, the pooling range is equal to plus minus 1 by 2 T coherent, 1 by 2 T coherent. So if you take T coherent as 10 millisecond, 1 by 2 T coherent, that will give you 50 Hz. 10 millisecond means 10 into 10 to the power minus 3, so 10 to the power 3 will come to top. So 10 to the power 3 divided by 20 you have to do, that will give you 50 Hz. For the ATAN discriminator, the pooling range is 1 by 40 plus minus 1 by 40. So in place of 1 by 2t, you have to do 1 by 40. That's why it is half. Okay. Now using these mathematical functions, all of these can be determined. Okay. So you just need to substitute the expressions of I and P and do simplifications. Then you will find that they are all functions of 8D. And then just plotting the functions for different coherent integration time will tell you how the pooling range is related to T coherent. So we see that the pooling range is inversely related to the coherent integration time. Or 10 millisecond in case of 8 and 2 discriminator, it is within plus minus 50 Hz. So this implies that after acquisition, the actual error must be within this range, pooling range. Otherwise, the tracking loop will not be able to bring the error to near zero with the help of negative feedback control. For example, after acquisition, in case of the A10 discriminator, if the actual error lies here, actual error is positive, but the discriminator output will be negative. As a result, we get wrong correction and the error will, instead of coming here, will come to this point. This causes false lock. Okay, locking means you are able to bring the error towards zero. When a loop is locked, it means that the corresponding error which you are trying to make zero is near zero. So when the error instead of coming here comes here, we call false lock. So we need to make sure after acquisition the error is within the pooling range of the discriminator. Now after acquisition, the error will not. It's not necessary that the error will be within plus minus 50 Hz or plus minus 25 Hz. So how to deal with that? So soon after acquisition, T coherent is not taken as 10 milliseconds. We take a small value, say 1 millisecond. If we take 1 millisecond, 1 by 2t will give you 500 Hz. So lower the coherent integration time, higher the pooling range. So you start tracking with lower coherent integration time, which will give a higher pooling range, and therefore with the help of negative feedback control, the loop will try to bring the error to zero. As tracking progresses, this can be increased. Increasing this means you are narrowing down the pooling range. Why would you want to do that? Because the lower the coherent integration time, it can be shown that the higher is the noise. In all these outputs, we have not included the effect of noise. These are all clean discriminator outputs, meaning we do not have this term, contribution from the noise terms. We have just considered this one and this one. It can be shown that the lower the coherent integration time, the higher eta will be. And we do not want eta to be very high. Therefore, to reduce eta, as tracking progresses, we reduce the pooling range and increase the coherent integration time, which in turn reduces the pooling range. And it is expected that by then the error has come in this region, so it should not affect. Okay. So here we see that the pooling range is about for 10 millisecond coherent integration time, it's about 25 plus minus 25 Hz or plus minus 50 Hz, depending on what discriminator you consider. So few cycles, 50 Hz means 50 cycles, 25 Hz means 25 cycles. How about the corresponding PLL discriminator, where we are trying to bring the carrier phase zero? So these are some of the PLL discriminator outputs. Along the x-axis, you have the actual carrier phase error, and along the y-axis, you get the corresponding discriminator outputs. And what is the pooling range here? The pooling range or the linear range, for some it is the same as linear range, is within plus minus 90 degrees. Within half a cycle, plus minus, within a quarter, not half. Plus minus 90 degrees means within a quarter cycle. So if delta phi is more than a quarter cycle, loop is not locked. In this case, the pulling range is within a quarter cycle. It is plus minus 2 pi by 4, 45 degrees. Sorry, plus minus 90 degrees. In other words, it is within half a cycle. Sorry, within a quarter cycle. Here we can tolerate higher error because the pulling range is few tens of cycles, whereas here the pulling range is within a quarter cycle. So these tolerates much less error. The PLL tolerates much less error. By design, the discriminator tolerates much less error, which implies it is more accurate. So when the PLL is logged, meaning delta phi is near 0, it is much more accurate because the pulling range is shorter. Whereas this one tolerates more error, so it is comparatively less accurate. This is why it is written that Doppler when PLL is logged is more accurate. So whether an FLL is logged or a PLL is logged, you can find the Doppler. But the Doppler that you will get from a PLL is much more accurate, about 10 times more accurate than the Doppler that you would get from an FLL, because it tolerates less error. But what is the downside? Downside is that to have the PLL logged, C over N naught must be good. Below 30 dBH generally for a traditional receiver, PLL cannot be logged because the error goes beyond the pulling range. So to have the PLL logged, C over N naught should be good. And also if the user moves fast, it has high dynamics. If it changes its orientation fast, turns fast, bangs fast, then also there is a higher chance that the error will go beyond the pulling range in case of the PLL. Whereas this can tolerate all these adverse situations. It can operate at low C over N naught because it tolerates higher errors. It can operate at low C over N naught. It can also operate when the user motion changes fast. So it can tolerate higher dynamics. It can tolerate lower C over N naught for quality signal environments. But it is less accurate. Okay, so this is less accurate but more robust. This is more accurate and less robust. Okay, that's all about the discriminators. Next, we'll quickly look at the numerically controlled oscillator. Here we have the numerically controlled oscillator for the code tracking loop, and here we have for the carrier tracking loop. So let's quickly see how these numerically controlled oscillators work and contribute to tracking. Basically, we'll first see the carrier NCO, numerically controlled oscillator. A numerically controlled oscillator or NCO needs to keep track of phase. Okay, now phase can be within plus minus pi or 0 to 2 pi, basically one cycle. So its job is to increment the phase of a cycle in steps from minus pi to plus pi or 0 to pi. Once it reaches the maximum value, it is reset to 0 and the cycle repeats. How can we increment the phase? It is driven by a clock. Okay, now the clock signal will be a series of square waves. So you get pulses from the clock, A pulse means it has a rising edge, it also has a falling edge, right? So by design, it can be made sensitive to the rising edge or falling edge. Let's assume that this NCO is sensitive to the rising edge of each pulse. So when the rising edge of each clock pulse occurs, phase will be incremented. And until the next rising edge, it will be held at that value. So what will be the step size? What will be the duration of each step? It is 1 by Fs because the frequency, clock frequency is Fs. There will be Fs pulses in a second. What will be the duration of one pulse? It is 1 by Fs. That's why the duration of each step is shown as 1 by Fs. Now when phase is incremented, how much will it be incremented? What will be the step size? That is determined by this input M. So every time when the rising edge of the clock pulse occurs, the phase is incremented by M. Okay. How does it happen? Let's understand quickly. There is an adder whose task is to add digitally. Okay. It has n bits. Each bit can be either 0 or 1, which means it can have 2 to the power n values. Each bit will be 0 or 1, right? And each bit is independent of the other, so you can have 2 to the power n combinations. So it can hold 2 to the power n different values. Okay. So when the rising edge of the clock pulse occurs, its content will be incremented depending on this m. And then until the next rising edge, the content is held constant in the holding resistor. So its job is to keep the value as it is. That's why we have this constant phase here. And then at the next rising edge, it will be again incremented. So adder increments, holding resistor holds it until the next rising edge. Let's understand how this happens with a specific example. Let's say n is equal to 3. So it can have 3 bits. And m is equal to 4. Okay, so here we see different contents of the adder. So we have 3 bits 0, 0, 0, 0, 0, 1. So these will be the different values that the adder can have. 0, 0, 1, 0, 1, 0. So 0, 1, 2, 3, 4, 5, 6, 7. After that it will be reset to 0. All are ones, it will be reset to 0. So this is how the adder keeps on incrementing its values. Now let's say it starts with this value. Then m is equal to 4. So at the next rising edge of the clock, it has to be incremented by 4. So 1, this is 1 increment, second increment, third increment, fourth increment. It will complete. What is the duration of this? This is 1 by Fs. Because each clock pulse is of this duration. When the next rising edge occurs, it will be again incremented by 4 and its content becomes 0. So overflow occurs and it is reset. It comes here again. So how long will be the cycle for this particular case? 1 by Fs, another 1 by Fs. Total duration is 2 by Fs. So it takes 2 by Fs seconds for reset to occur. That means the duration of a cycle is 2 by Fs. If the duration of a cycle is 2 by Fs, frequency will be inverse of that, Fs by 2. So we get Fs by 2. Basically, it will create a cycle whose frequency is Fs by 2. Now in general, the output frequency is related to m and n this by this fs into m by 2 to the power n. You just substitute for m and n. In this case n is 3, so 2 to the power 3 is 8, m is 4, so 4 by 8 fs by 2. And from the example also we saw that the frequency is fs by 2. So for this particular combination the output frequency is fs by 2. In general, for some m and n, it can be shown that the output frequency is fs into m by 2 to the power n. So what will be the minimum output frequency? So for minimum output frequency, we need to take m is equal to 8. Sorry, m is equal to 1. So if m is equal to 1, it will be just incremented by 1 at each clock edge. So next clock edge occurs, it will come here. After that it will come here, and then it will come here, 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 here. So how many 1 by fs will be there? 1, 2, 3, 4, 5, 6, 7, 8. 8 by 8 by fs. The total duration before overflow occurs is 8 by fs. The inverse of that will be fs by 8. So that will be the minimum output frequency. fs by 2 to the power n is the minimum output frequency that you can get from this NCO. This is called the frequency resolution. Minimum output frequency. What will be the maximum output frequency? See, for any cycle, we need at least 2 points, right? At least 2 phases we require. This means the frequency m, so the maximum frequency that we can have is fs by 2, which means m will be 2 to the power n minus 1. In this case, n is 3, 2 to the power n is 8, and m will be 2 to the power n minus 1. n is 3, 2 to the power n minus 1 is 2 to the power 2, which is 4. And we are getting fs by 2. fs by 2 will give us at least 2 points. We need at least 2 points, one from this part, one from this part. Otherwise, if you just take one part here, 1 point here, and there will not be any point from the other half. We need at least 2 points. So the maximum output frequency that we can have is fs by 2. Minimum that we can have is fs by 2 to the power n. Okay. Now once we generate the phase, if it is fed to the cos function or sine function, we get cos or sine. Where does it fit? It fits here. So to generate the replica carrier NCO will give phase. Now you use cos or sine and you get the corresponding cos term and sine term. So cos term is actually the replica carrier and this is the sine equivalent, so that we get 2 components, in phase and quadrature phase. In general, for a receiver, the typical value of fs is about few hundred megahertz. So let's consider 200 megahertz. Okay. And how many bits will the adder have? 32 bits or 64 bits. So it can hold 2 to the power 32 bits, it can hold 2 to the power 32 values. If 64 bits, 2 to the power 64 values. So using these values, you can find the minimum and maximum frequency. Here it will be 200 megahertz divided by 2 to the power 64 if there are 64 bits here, minimum frequency. And then maximum frequency that we can have is half of fs. So 100 megahertz is the maximum frequency that we can have, and minimum frequency is fs by 2 to the power 64 or 32. Now what output frequency do we want? We want to generate this replica carrier after it is down converted. So what is the frequency? FIF, intermediate frequency, plus Doppler. What is the order of the intermediate frequency? After down conversion, generally it will be few megahertz or maximum few tens of megahertz. It will not be more than that. And what will be the order of Doppler? Doppler will be few kilohertz. In case of GPS or IRNSS, it will be within plus minus 15 kilohertz. For GPS, plus minus 10 kilohertz. Within plus minus 10 kilohertz. For fastest moving aircraft, it will be around 10 kilohertz. Okay, for GPS. And for IRNSS, about depending on which carrier frequency you are considering, from plus minus 8 kilohertz to plus minus 15 kilohertz. So basically, we do not require anything more than few megahertz plus minus few kilohertz. That is what we want. And it lies well within the range that the carrier NCO can generate with say 200 megahertz clock and 32 bits or 64 bits adder. Okay. Now, how can we use the carrier NCO to make corrections? Based on the loop filter, the preceding component is the loop filter here. Based on the loop filter, M value is adjusted. Okay, so that at the output we get the correct IF and correct Doppler. IF will be constant after down conversion. It is the Doppler which has to be corrected. So by suitably adjusting M, depending on the loop filter corrections, we can correctly find the Doppler and generate the output frequency. This is how, with the help of carrier NCO, we can correct the Doppler. Okay. How about the code? In case of the code NCO, the phase is maintained the same way. It is incremented at the clock rising edge or falling edge, and it has some zero minimum value or maximum value. After maximum value, it is reset. But the carrier NCO, the code NCO keeps the phase of a chip. Here we have no cycle because we are not dealing with any sinusoidal wave. Here we need to deal with chips. So it keeps the phase of a chip, fraction of a chip. When overflow occurs, it sends out a high signal. And this increments the code generator by one chip. The code generator keeps the current chip. So we know that in a code epoch or code period, there are a number of chips, capital N chips are there. The code generator holds the current chip in the code period. So it will output the value of that chip, either plus 1 or minus 1. That will be output from the code generator. And when the code NCO overflows, it is incremented. So together, we get the number of chips in the code period and the fraction of the current chip here. This is where it lies in the loop. So if this is the current chip, the code generator will hold the current chip and output the value of the chip. Okay, and the code NCO will tell you a term here, the fraction of a chip. The fraction of a chip, which point in the current chip at present it is in. So that will be obtained from the code NCO. What is the current chip number? that will be kept in the code generator. Okay, so with the help of code NCO and code generator, it is possible to find out the code phase of P or how much time has elapsed, because TC has a particular time, right? So N is the number of chips preceding the current chip since the beginning of the code period. A is the fraction of the current chip. So with the help of the code generator and code NCO together, we can find the code phase of this point. Let's say this is the current point. In other words, we can find the time between this point and the beginning of the code epoch, because each chip has a particular duration, TC. Now, how can we correct this? So the loop filter sends some corrections based on which the M value, capital M value, here also we have capital M value is adjusted, and that will adjust the fractional part here. So this way we can make corrections to bring tau to 0. Okay. Now here we have two loops, code tracking loops and carrier tracking loops. We have talked about the discriminator. We have also talked about the corresponding NCOs in the loops. We know that in case of the code tracking loop, the code phase discriminator or DLL discriminator gives the code phase error, a value of tau, right? So here we get the code phase error. In case of the carrier tracking loop, if the Doppler is tracked, then we get delta FD. If the carrier phase is tracked, then we get delta phi. Now, under some assumptions, this loop can be reduced to a block diagram representation with transfer functions. How does it look and when can we do that? We can make such transformation only when the discriminators operate within the linear region. The only nonlinearity here is, in this part. So this gives some tau, this gives some delta phi or delta FT. And if we can reduce the if the discriminator operates in this linear region, then we can transform this complicated loop into a simplified block diagram as follows, like this. So this summation block actually shows that nonlinear discriminator operation, and that's why it is put within double quote. It's not actually linear. Under certain circumstances, when the error is small, lies in this range or here, we can do this. Here. We know that the output will be error. What is the error? If we are interested in code phase tracking, it is tau. If we are interested in Doppler tracking, it is delta FD. This is the discriminator output. If we are interested in carrier phase tracking, it is delta phi. So depending on which loop you are running, this will be either tau or delta FD or delta phi. So this point here actually corresponds to this one, here and here. So it has two inputs. One is the incoming parameter, signal parameter. So if you are interested in code phase tracking, it is the incoming code phase. And the other one is the reverse of what the receiver calculates. So if it is code phase tracking loop, this will be incoming code phase CP, and this will be negative of CP hat. We know that the difference between CP and CP hat is tau. The output is tau. The discriminator provides a value for tau, right? Discriminator output in the linear range, the It is the same as the actual tau, right? If it is a Doppler tracking loop, this is the incoming Doppler, actual Doppler frequency of the signal, and this is what the receiver generates, FD hat. This will be FD, this will be FD hat, and the difference is delta FD. If it is a carrier phase tracking, this will be the incoming carrier phase. This is what the receiver replica says, and the difference is delta phi here. So depending on which parameter you want to track, the loop will change its value. Okay. Now, what kind of time profile we can expect for the input, whether it is code phase or Doppler frequency or carrier phase? What kind of temporal variation can we expect? So this is dependent on the user and satellite relative motion. Okay. So depending on the relative motion between the two, either we can have step, typically one of the three profiles is obtained, step, ramp or parabolic. Okay. Generally we get step and ramp because satellites are far away, but parabolic is also possible. And for some complex dynamics, we can get combination of these or some other profiles. But generally, it is one of the three. Whether you consider code phase or Doppler or carrier phase. Typically within the first two. Okay, and with the help of a tracking loop, we need to track this. This is the loop filter. Now, since everything is linear, we can have a transfer function representation. The loop filter transfer function is f of s. What is the function of the loop filter? See, when the input comes here, noise is always present. In this case, we cannot avoid noise. Noise is always present. So the loop filter needs to filter out noise to the extent possible. It should also shape the transient and steady state responses of the loop. So the loop filter should be chosen such that it has satisfactory transient and steady state performance. At the same time, it filters out noise. Okay. Now I'll come to this additional later, summation block later. Okay, for the time being, just ignore this. Assume that this goes directly to the NCO. We know that the NCO generates basically the replica code or carrier. The traditional receiver uses some fixed transfer functions for the loop filters. Okay, loop filters are typically type 0, 1 or 2, depending on which parameter you are talking about, code phase or Doppler or carrier phase. So this for DLL or PLL, this is the form of the transfer function. For code phase tracking and carrier phase tracking, this type of transfer function we use for the loop filter. For FLL, this is what we generally use. S is the Laplace variable. C is some coefficient. Okay. In the traditional architecture, C is predetermined. Okay. C is optimally determined and used. But some sophisticated design can also vary C, depending on C over N naught, signal to noise environments, and user motion. Okay. That is also possible. How about the transfer function of the NCO? What transfer function should be used for the NCO? For that, we need to understand the input and output of the NCO. We noted that M is adjusted based on the loop filter corrections. How is M related? M is actually proportional to frequency, output frequency. And M is corrected based on loop filter output. Since the output frequency is proportional to M, we can say that the loop filter sends some frequency correction to the NCO. Because M is adjusted based on the loop filter output. Okay, based on loop filter output, capital M is adjusted. And we know that the output frequency is proportional to capital M. So we can say that some frequency correction is sent by the loop filter to the NCO. The input is some frequency correction. How about the output? If we are doing code phase tracking, output has to be code phase. If you are doing carrier phase tracking, then also output has to be phase. So input is some frequency correction, output is phase. We know that frequency is the derivative of phase. So we need to do integration here to get phase from frequency. That's why for DLL or PLL we have 1 by S. Because input is some frequency correction, output is phase. We need to do integration to get the phase. In case of DLL or PLL, code phase loop, this is carrier phase tracking loop. How about delta FD? Frequency lock loop. We send some frequency correction, output is also frequency. So in this case, we consider unity. No integration, nothing is required. Just match the unit at the input and output. It is unity. Input is also frequency, output is also frequency. So in case of the FLL, the transfer function for the NCO is 1. So with this, if we ignore this summation block now, we can find the closed loop transfer function H of S, right? So this is the H of S, the closed loop transfer function. Now see, the loop has two objectives. Filter out noise to the extent possible. Also have satisfactory transient and steady state performance. So the loop bandwidth has to be adjusted in such a way that it filters out noise. At the same time, it has desirable response. Now we know that if the loop has to track the changes fast, it should have high bandwidth. But if it wants to remove noise, it should have low bandwidth. The lower the bandwidth, the more will be the noise eliminated. But at the same time, it cannot track the changes fast. To track changes fast, bandwidth should be high. To remove noise, bandwidth should be low. So there is a trade-off. Okay, it has to do a trade-off. Now to make the loop operate better, some aiding can be provided. How the aiding can be generated? See, the loop has to track these changes fast. What if we can feed these changes from some external means? That is what is done. So if we can have another sensor, say an inertial navigation system, that can sense the user motion. So this profile is largely dictated by the user motion. So the INS can generate the user motion, and then we, from the ephemeris, we have some idea about the satellite motion, so we can actually predict the Doppler and feed that. So if this external information comes, then the task of the loop becomes easier because it does not have to track all the changes on its own. It is getting some aiding. So whatever error is there in the aiding, only that residual part has to be tracked by the loop on its own. So in that case, it can reduce the bandwidth and eliminate noise more. This way, by providing external aiding, we can make the loop operate better. Operating better means it can narrow down tau further. It can provide more accuracy. It can operate at lower silver and not environments. It can operate in higher dynamics, meaning this if this changes fast, then also the loop can operate properly if we can have some external AD. That's why this summation block is shown here. Any question? Anything that you could not follow about tracking, discriminator, NCO, or overall operations? No question? If you have any question, feel free to ask me. If you did not follow something, feel free to ask me. Are you afraid to ask, or you indeed have no question? That also you cannot say. You don't have any question, or you did not understand anything. What is it? Nobody wants to volunteer to respond. You do not want to respond in the last class also. Okay, fine. So next is navigation, data demodulation, and measurements generation. This is the last part under ranging processor. When DLL and PLL are logged, meaning tau is around 0, delta phi is also around 0, it is possible to extract D. We discussed this earlier also. So in that case, this becomes 1, this becomes almost 0, so this is 1. If delta phi is 0, delta FD also has to be 0. You cannot make phase 0 without making frequency 0, frequency error 0. When this is 0, sync function is 1. If tau is around 0, R of tau is 1. Generally, this term is much larger than noise. We ignore noise at this point. The only sign that only term which can change its sign is D. So the sign of in-phase prompt correlator will give the data bits. So this way we can extract the data bits from the sign of IP. Next, how can we generate the pseudo-range and pseudo-range rate measurements? So we assume that DLL is locked. Locked means tau is near 0, code phase error is 0. The near 0 tau indicates that the replica prompt code is almost aligned with the incoming code. So here we see the black as the incoming code and green is the replica code, replica prompt code. So green is almost aligned with the black. The black was generated by the satellite. Satellite generated the black, the incoming code precisely at particular time instance and transmitted. That time is the time of transmission. Now since the receiver is able to align the prompt code almost properly with the black, we can treat the prompt generated by the receiver is almost the same as the one that the satellite generated. Now to find the pseudo range, we need two times, right? C into TR, time of reception, minus time of transmission. So let's assume that at some point, this is the, at some time instant, this is the point, current point of the code. And at this point, we want to find the range to the satellite, pseudo range to the satellite. So this point was received by the receiver at TR. How can we find TR? TR is obtained from the receiver clock. Now at what point the satellite transmitted this? That is the time of transmission, and the difference between the two is the travel time. Multiplying that with the speed of light will give the pseudo range. So the task here is to find TT, time of transmission. At what point, what time this point was transmitted by the satellite. TT has two parts, okay? T naught plus TP. T naught is a coarse component, whereas TP is a fine component, okay? We get T naught from the navigation data, and TP we get from the code generator and NCO. How and what are they? So this is some point in the current chip. Where does this chip lie relative to the beginning of the current code epoch? That information can be obtained from the code generator and NCO. How? We know that the code generator holds the current chip. So from there we'll get to know how many chips have passed since the beginning. If this is say n plus 1 chip, then n chips have already passed. We know the duration of each chip, it is TC. So until the beginning of this chip, how much time has elapsed from the beginning of the code epoch? It is n times TC, the number of chips before the current chip since the beginning of the code epoch. We know that is n. So n times TC is this much time. How about this fraction of the chip? That information we can get from the NCO. The code NCO keeps track of the fraction of the current chip. So this information we get from the NCO. How many chips have already passed? That information we can derive from the code generator. So this way, with the help of the code generator and the NCO, we can find this time. And TP is that time. The time that has elapsed since the beginning of the current code period or current code epoch. Next, the task is to find the time at which the beginning of the current code epoch occurs, which is T naught. This time we can obtain from the navigation data. How? We know that in case of GPS and IRNSS SPS signal processing, GPS L1 and IRNSS L5 or S, each navigation data bit is 20 milliseconds long. And the navigation data bits are designed in such a way that you get to know, once you demodulate and decode the navigation data, you can find the time of each of this bit. So each is a bit, okay, navigation data bits. Each is 20 milliseconds long, and by decoding the navigation data, it is possible to find the beginning of each navigation data bit. So we know precisely at what time this bit was generated in the satellite, at what time this bit started, at what time this bit started, and so on. So by extracting and decoding the navigation data, we know this time instance. Now expand one bit. It is 20 milliseconds long. We know that the CA code epoch is 1 millisecond long. So one navigation data bit can accommodate 20 code epochs. There will be 20 code epochs. Each is 1 millisecond long. And since we know the time of start of the bit, we know this time. This we know from the navigation data. Now, if we keep track of the code epochs that have elapsed until the current epoch, we will be able to find the beginning of the current epoch. For example, let's consider the current epoch is the second epoch. We get this time instant from the navigation data by decoding the navigation data. After that, just 1 millisecond has passed. So that time plus 1 millisecond will give the beginning of the current code epoch. And this time is nothing but this time. Similarly, if we have some mth epoch as the current epoch, we know before the mth epoch, m minus 1 epochs have passed, right? Each epoch is of 1 millisecond long. We know the starting point here from navigation data. And then to that we need to add m minus 1 milliseconds. That will give us the beginning of the current code epoch. So this way we can find T naught. With the help of navigation data bits, we can find T naught, and TP we can obtain using code generator and NC. So this gives us the time of transmission. And all this is possible only when prompt is aligned with the incoming code. Prompt is aligned with the incoming code means tau is near 0. Code phase tracking loop is logged. Code phase tracking loop will not be logged if PLL or FLL is not logged. So either PLL or FLL has to work properly for the tau to be 0. It is not possible that tau is 0 here and delta FD is very large. That will not happen. They are coupled, okay? Although we have not shown that coupling, but because we have assumed linear operation, and they are coupled. So only when the tracking loops are working properly, DLL and FLL or DLL and PLL, you can generate the pseudo range measurements. Otherwise, you cannot. Next, how to generate the pseudo range rate measurement. Pseudo range rate is related to Doppler this way. You derive this expression in the class, how Doppler is related to relative motion, change in the rate of change of range. Pseudo range rate is basically minus C by FL into FT. This is the Doppler. FL is the carrier frequency, C is the speed of light. So we know C and FL. We need to find FT. FT is a frequency. It is the rate of change of phase minus FF, IF. How can we get the rate of change of phase? We know that the carrier NCO keeps track of the phase, right? So at two successive time instants, we can extract the carrier phase output from the carrier NCO. Difference the two. Divide this by the corresponding difference in the time instants. The separation between them will be small, okay, on the order of few milliseconds. So if it can be 1 millisecond apart, 2 millisecond apart, 10 millisecond apart, like that. Very small time difference. So this will give the rate of change of phase. The rate of change of phase is equal to the frequency. What is frequency? Frequency is FIF plus Doppler. So this term is FIF, the intermediate frequency, plus Doppler. If we subtract the FIF from this, we get Doppler. So this way we can find the pseudo range rate measurement. Now in case of carrier tracking, we have two possibilities. Either a PLL is logged. When a PLL is logged, this is the incoming carrier and blue is the replica carrier of the receiver. When a PLL is logged, blue and red are aligned. They are synchronized. So when FLL is logged, They will not be phase synchronized, but they will have the same frequency. So there will be a fixed offset between red and blue when an FLL is logged. But we are interested in the difference. So the carrier NCO actually gives the phase of the blue, the receiver generated replica. If there is a fixed offset between the incoming and the receiver generated, in the difference that offset gets cancelled out because both will have the same offset from the red. Both phases will have the same offset from the red. So the offset gets cancelled out, okay, and we can find the Doppler. So whether a PLL is logged or an FLL is logged, whether we are doing carrier phase tracking or carrier Doppler tracking, we can always generate the pseudo range rate measurements. But when a PLL is logged, pseudo range rate measurements are more accurate. As I noted earlier, Doppler is more accurate because the corresponding discriminator allows less noise. It can tolerate less noise. So the pseudo range rate measurements that we get when a PLL is logged more accurate. So this explains to you how the pseudo range and pseudo range rate measurements are obtained. I do not know whether you could follow anything because you do not seem to respond at all. But since there is a time constraint, I cannot get into that anymore. If you have any questions, feel free to ask me. Otherwise, we'll have a 5-minute break. And after the break, I will quickly discuss the ranging process, the navigation processor, and that will be the end of the class. That's it. Let's have a 5-minute break and we'll resume our discussion at 12:14. Okay, we have come to the last stage of the receiver, which is the navigation processor. Uh, so here we'll basically talk about the order of magnitude of different measurement errors and then see the implementation of the navigation filter. In particular, we'll see how the measurement models can be obtained for the filter, and then we'll quickly see the equations of EKF and WLS. We'll not go into the equations because we already discussed this in the class. Uh, so we'll not discuss the filter equations in detail. We'll derive the models uh, and then just look at the filter equations. Okay. So what are the orders of different measurements errors, pseudo-range measurements error? So basic objective of the navigation processor is to generate the user position, velocity, and receiver clock error. Estimate the user position, velocity, and receiver clock error. So in this class, we will see how that is possible when the pseudo-range and pseudo-range rate measurements are available. So when the carrier phase is tracked, we can also generate another type of measurement called accumulated delta range, which is much more accurate than the pseudo range. Okay, but this is available only when the carrier phase tracking uh, is possible. So we have not discussed anything about the accumulated delta range, so we will not consider accumulated delta range in further discussion. So here we will see how using the pseudo-range and pseudo-range rate measurements, we can estimate the user position, velocity, and receiver clock error. Okay. Now before getting into that, let's quickly understand the order of errors. We know what are the different sources of error in the pseudo-range measurements. We discussed this many times in the class. Now we'll quickly see the order of magnitude for different errors. We know that the satellite position can be obtained from the navigation data. The ephemeris, satellite orbital elements are broadcast in the navigation data. When the receiver demodulates and decodes the navigation data, it can receive the ephemeris from the navigation data. But the broadcast ephemeris is not as accurate as precise ephemeris. Okay, precise ephemeris can be obtained from the internet after some days. Okay, but the ephemeris that the satellites broadcast are not as accurate. So they have some inaccuracy. Generally, the order of error in the satellite position that we can generate using the broadcast ephemeris is less than a meter. Okay. Satellite clock error from GNSS system time is on the order of 10 to the power minus 9 seconds, less than that, because the clock on board the satellite is steered by the master station, but still it will have some small drift from the system time, and uh, it is actually broadcast in the navigation data. Okay. So the receiver can remove this clock error from the pseudo-range measurements by getting the parameters, relevant parameters from the navigation data. Okay. This is small and it can also be removed from the pseudo-range measurement using the information given in the navigation data. Now we know that ionospheric error plays a major role in the error, pseudo-range measurement error. It is the most dominant component generally. Using dual frequency measurements, the receiver can eliminate the ionospheric error completely. We discussed this in the class. But if it is a single frequency user, then the user has to use some model, mathematical model, to partially remove the ionospheric error. There will always be some residual component after that. That residual ionospheric error is on the order of 2 to 4 meters when the ionosphere is behaving normally. Okay. During ionospheric storms, during rapid buildup of electron density in the ionosphere, the error can be much larger. Then what is the order of the residual tropospheric error? We know that the tropospheric error cannot be removed using dual frequency measurements. So the user has to apply some mathematical model to partially correct the tropospheric error. The residual tropospheric error, after applying the correction using the user model, will be on the order of a meter. But this varies with elevation angle. Even the ionospheric error also varies with the elevation angle. And what is the receiver clock error? The receiver clock error is a few thousand meters. When you generated the plots for the receiver clock error, you saw the error. You saw some kilometer level error. But fortunately, the receiver estimates it out. Otherwise, it would have been impossible to derive position, user position with such an inexpensive clock. Okay, but the error also depends on what kind of crystal oscillator you are using, whether it is a TCXO or CXO or chip scale atomic clock. That also affects the order of the error. Then there will be always some noise. That noise, if the signal reception occurs in an open environment, is on the order of 1 meter for pseudo range measurements, which we derive using the code. What do I mean by when I say derive using code? See, the time of transmission was partly generated by the code generator and code NCO, right? And that will be of the order of millisecond. That component is coming from code. That's why I say that pseudo range measurements are generated by code. Okay. Next, multipath. We know multipath is the reflecting signals received along with direct signals. Now, multipath largely depends on the signal reception environment. I have given some typical value, but if the signal reception environment is not good, it is if the receiver is surrounded by high-rise buildings, trees, or there are some structures nearby which can easily reflect signals, then of course multipath will be much larger. It also depends on the delay between the reception of the direct signal and the reflected signal. If the reflected signal is received much after the direct signal, then the chance of error is much less. Okay, but if the multipath is received shortly after the direct signal, then there is a chance of more error introduced. And how much error will be incurred by multipath also depends on what kind of signal you are processing. Okay. So these are different sources of measurement errors, and here we see their order of magnitude. With this in mind, let's get into the filter. Filter means we will not derive the equations that we already derived. We'll just see quickly how to implement the filters that we derived in the class earlier, apply here. So to apply the filters, generally use the weighted least squares or extended curl filter. Extended curl filter because there is some nonlinearity. Measurement models are typically nonlinear. Okay, So here we'll see how to derive the models which we can use in the filter equations. So we'll start with the pseudo-range measurement. We have two measurements, pseudo-range and pseudo-range rate measurements. We assume that navigation data has been decoded by the receiver and the navigation filter has the satellite position calculated from the ephemeris, the orbital elements. Okay, so we assume that the satellite position is known to us, although with some imperfection, there is some error, but the satellite position is known. We are not going to treat this as unknown. The pseudo-range measurement from satellite eye to user is given by this. We looked at this many times. R is the true range to the satellite. BU is the receiver clock error in meters. BS is the satellite clock error in meters. Since the receiver can eliminate this clock error, we will not consider this in our subsequent discussion. Or in other words, we can account for it in later equations. Okay. Either we can remove this at this point or we can account for this in later equations. But this is a known quantity to us, satellite clock error. Then the ionospheric error or ionospheric delay in case of the pseudo-range measurement, which is derived from code. Tropospheric delay, tropospheric error. This represents multipath and then noise. The receiver, based on its guess, can predict the pseudo-range. How? It knows satellite position from the ephemeris. It has some guess of the user position. We know this is how range can be obtained using satellite position and user position. XS, YS and ZS are X, Y and Z coordinates of the satellite position. XU, YU and ZU are the user coordinates. So with some guess, the receiver can predict the range. This is the true range, this is the predicted range. So in the predicted pseudo-range equation, we have the predicted range. And with the knowledge that the receiver has, it can predict the receiver clock error. Satellite clock error can be derived from the navigation data, obtained from the navigation data. That's why no hat term for satellite clock error, it will be removed. I hat is the, we assume a single frequency user. I hat is obtained using some mathematical model, user model for the ionospheric error. T hat is obtained from the mathematical model. So all these will give the predicted pseudo-range. The difference between the two is the pseudo-range measurement innovation. Innovation is the term that we use in the context of Kalman filter. Okay. In case of weighted least squares, we take the difference, but we do not call it innovation. Okay. We just say that some residual pseudo-range measurement for the weighted least squares. So it's basically the difference between actual pseudo-range measurement and predicted. So if we take the difference, here we have R minus R hat, B minus BU minus BU hat, that will give the delta BU. Then we have, this will be eliminated, I minus I hat, T minus T hat, epsilon and eta. So all these are clubbed in this measurement error term. This is the measurement error. And it is modeled statistically. So generally assume Gaussian distribution, okay, of mean 0, and let's say the covariance is R. Now here we have some nonlinear equations, right? R is a nonlinear function of x, y, z. Similarly, R hat, x hat, y hat, and z hat, right? So R minus R hat we can express as a Taylor series, correct? and then take only the first order term. So if you do the Taylor series expansion, so we have these expressions of R and R hat, and if you do the Taylor series expansion, first order Taylor series expansion, R and R minus R hat will be this. So you just need to follow the procedure for Taylor series expansion and then collect the terms. Okay, so this is XU minus XU hat, and there will be a corresponding term for this. Similarly for the Y component, Z component here. So you're basically taking derivatives with respect to XU, YU, ZU, and then XS, YS, and ZS. The corresponding difference between actual and predicted is shown here. Since we know the satellite position with some imperfection from the navigation data, the derivative is also taken with respect to the satellite position. Okay. Now, as per the actual Taylor series expansion, here you have to use XS and XU. But then this will be unknown. We do not know actual satellite position. We have some satellite position from the navigation data. We know that is not accurate. It has some error. But here we need to use the satellite position. We also need user position. So what can we do? We can use the guess or the knowledge that we have. This X hat, Y hat, and Z hat, this actually obtained from the navigation data. So use them. And XU hat, YU hat, and ZU hat, they are actually receiver's guess. So using these, we find these terms here, and then these are errors. Error in the X coordinate of the user position, error in the Y coordinate, error in the Z coordinate. Similarly, error in the X coordinate of satellite, Y coordinate, and Z coordinate. Now, this one, and this one, we can write in a vector form, okay, and represent as UI. This is actually the unit vector pointing from the user to the satellite. So this is the satellite position, this is the user position in the X direction, Y direction, Z direction. We are dividing that by the range. So you are basically getting the unit vector pointing from the user to the satellite. This is also called the line of sight vector. Okay. Now we are using X hat here and here also. R also we are using predicted range. But this does not introduce large error because the satellites are far away. Okay, R is much larger than the numerator. Here we take the difference. It can be shown that the denominator is much larger. So any small error, how much error will you introduce in the numerator? Few meters. It will not be more than that because we know that satellite position is accurate within a meter, and the user has to start with some reasonable guess, or it can with iteration it can go close to the truth. So the error will be few meters, few tens of meters at most we can take. Even if we take 100 meters, that is less because what is the order of R? R is some 20,000 to 30,000 kilometers. So on the top, you have some say 100 meters error. 100 divided by 30,000 kilometers. If you do, how much error will you introduce? Very small error. So although we do not know the truth here, and we are using what we know, the error introduced by doing this is negligible because the denominator is much larger than the error that you introduce. Okay. So we can now write this in vector form. So this and this we can group together as minus ui, and then here we have delta bu. So we have done Taylor series expansion of the range difference term. We also need to take into account delta bu because in delta rho we have delta bu. So here we put 1 because of delta bu, and then this delta capital X is given by this one, delta xu, delta yu, delta zu, and then delta bu. Because of delta bu, this 1 is coming here. Similarly, for the last 3 terms, we can have just u, because you have the same elements as this one in the last 3 terms. But in place of delta x, we need to write delta xs. Delta xs is basically the error in the satellite position that we derive from the navigation data. Okay. Now we know that this error is on the order of a meter. We generally model this quantity statistically and put in eta. So including this term statistically in eta, we actually have this model. Delta rho I is given by this times delta x. This is unknown to us. And then this is the measurement error which we need to model statistically. We already used the Gaussian distribution, zero mean, error covariance R. R needs to be chosen appropriately based on this orders of magnitude. Now this we did for a particular satellite, ith satellite. There will be a number of satellites. So it's stacking all delta rho s for all the satellites. Visible satellites means satellites which are tracked by the receiver. We actually have a vector of dimension n. So let's assume that there are n visible satellites. So we have a vector of dimension n on the left side. And then on the right side, we have to write all the u and 1, u vector and 1 in each row. So this has 3 elements and this is 1. So basically we have 4 columns and n rows. Okay, and then delta x remains the same for all the satellites. User position error will remain the same for all the satellites. And then similarly we need to stack the noise, the error term. This is for the ith satellites. We need to stack all the eta terms for all visible satellites, and that will give this vector. Now putting bar underneath denotes a vector as per the convention of this presentation. So when we put a bar, it represents a vector. So this is a vector. We have transposed it. The vector we have transposed, it has become a row vector after transposing. It is a column vector, transposing it becomes a row vector. This is also a vector. The dimension of the matrix is n cross 4. There are 4 columns. What is the dimension of delta x? See, 4 elements are there. It is also a column vector. I put transpose here. So this has 4 elements, 4 by 1 vector. So n cross 4 times 4 cross 1, we get n cross 1. Here also n cross 1. N satellites, so n measurement error terms will be there. This is also an n cross 1 column vector. Now we can put the left side as delta rho bar underneath. Capital H is the matrix. Matrix is written as bold letters. So capital H bold is actually a matrix. When you put a bar underneath, it denotes a vector. When we write a variable in bold letters, it's a matrix. Okay, so capital H is a matrix. It's called geometry matrix, and then we have the measurement error, which is Gaussian distributed with zero mean and error covariance given by R. So this is the measurement model matrix. We started with nonlinear range measurement, and then using the first order Taylor series expansion, we have found a linearized measurement error model, linearized measurement model. And we need to do the same for the pseudo-range rate measurement model. Pseudo-range rate is basically the time derivative of the pseudo-range. This is the pseudo-range. If you take the time derivative R dot, bu dot is actually the delta t u dot, the drift of the clock. Bs dot, very small, can be corrected. I dot, generally when the ionosphere is well behaved, I dot is very small, can be neglected or clubbed in eta. Similarly, T dot can be neglected or clubbed in eta. A multipath will not be dot. Okay, multipath affects pseudo-range rate also. This has to be statistically modeled. Now we can ignore the dot terms for this, or we can model all of them statistically in eta. Okay, the predicted pseudo-range rate has to be obtained the same way. R dot hat bu dot minus bs dot. The other terms we do not consider any derivative of other terms. This is for the predicted pseudo-range rate. Then the same thing has to be done, the difference between the pseudo-range rate measurement and predicted pseudo-range rate has to be taken. So again here we have R dot minus R dot hat for the ith satellite, delta bu dot, corresponding measurement error term, again Gaussian distributed with zero mean and some error covariance. What is R dot? This is R, geometric range or true range to the satellite. Time derivative of R dot is, time derivative of the range is R dot. If you do the time derivative, you will find that it is a function of satellite velocity and user velocity. Okay, let's do the time derivative. We cannot do time derivative yet. We just need to do find the derivative with respect to time. You will find that it is a function of satellite velocity and user velocity. Satellite velocity we can obtain from the navigation data as before. The user velocity is not known. We want to estimate the user velocity. Okay. Just like this range difference, here also we need to do range rate difference, and then rearrange the terms, follow the same procedure as before. And then here we will get the user position error in the x coordinate, in the y coordinate, in the z coordinate, and the user velocity error in the x coordinate, y coordinate, z coordinate. Similarly for satellites. You just need to do it on your own, and you will find that you will get this expression. Okay. Following the same method as before, we can put it in this form. We have delta x s dot, the velocity, satellite velocity error. It is small, and it can be statistically modeled in eta. So finally we get this one. Again here also we will get u. Okay, u is there because we again have the same components. So stacking all the visible satellites, we get similar equation, vector equation, and this is the final form that we can have. for the pseudo range rate. Okay. Now you need to do this by hand, otherwise you will not be able to understand. Then we just need to apply the filter equations. We have got the measurement model, linearized measurement model. Next we need to just apply the filter equations. So you can have either weighted least squares and or Kalman filter, extended Kalman filter. This is the state space model. We want to estimate this. Italicize X. This is the state vector. What does it contain? So it is the X coordinate of the user, Y coordinate, Z coordinate of the user in ECF. In this form, we assume ECF user position, receiver clock error, user velocity, XU dot, YU dot, ZU dot, XYZ components of the user velocity, then clock drift, time derivative of BU. This is the clock error, the clock time offset from GNSS system time, and this is the rate of change of that. So these are the quantities that we want to estimate, and we put all of them under X bar underneath. So this is the state vector which we want to estimate. Now what is this A matrix? The A matrix takes this vector from time instant k to time instant k plus 1. So it basically captures how these quantities vary with time. We use a simple kinematic model. So if at some time instant k, if the x coordinate is xu k, what will be its position or x coordinate at time instant k plus 1? We know the velocity xu dot. Xu dot into the time interval will take it to the next time instant. And if we do this for all the y, z, even for bu, and put that in a matrix form, A will be a state transition matrix given by this. You need to do this by hand, otherwise you will not be able to you will not feel comfortable with this. Okay, and the M matrix is here is given by capital T. Basically, we are predicting or propagating X, Y, and Z from one time instant to the next time instant using the corresponding velocity terms, and then rearranging everything in a matrix. Okay, so this is the state transition matrix which takes this X vector from time instant k to time instant k plus 1. And here we are using simple kinematic model. We have not considered any dynamic motion. Simple kinematic model relating position to velocity or clock error to clock drift. We know the equations for the extended Karl filter for the weighted least squares. We just needed the A matrix, state transition matrix. We also need a linearized version of this H function, which is a nonlinear function that we have already got for delta rho and delta rho dot separately. Here we need to put them together, delta rho and delta rho dot. That becomes the linearized measurement model matrix. Okay. As for the weighted least squares, suppose we have got some x at some time instant k. Then using the state transition matrix, we can take it to the next time instant. And then apply the weighted least squares equations. Estimators are included in the exam, so there will be questions on estimators. Don't think that there will not be any question on estimators. So this way we will be able to update the estimate. And then in case of the extended Kalman filter, A we have got here, H we have already linearized, and this is the measurement model matrix considering both delta rho and delta rho dot. Each will give some H here. The first corresponds to delta rho, second H corresponds to delta rho dot. So since we have all the models, we can implement the filter with some initial guess. We have to start the filter. Now, in case of GNSS, we can actually start with zero guess. So we can assume 0, 0, 0, all 0. Okay, but then at the first time instant, we need to do multiple iterations. Some 7, 8 iterations we need to do using the weighted least squares or simple least squares. In weighted least squares, we have to weight using the measurement error covariance. Simple least squares R can be taken as identity matrix. So with multiple iterations, we will be able to converge to some estimate. Okay. How can we find whether we have converged or not? We take the difference between the current estimate and the previous estimate. If the difference is less than some tolerance, we say that convergence has happened. In case of GNSS, generally with some 5-6 iterations, it is possible to converge. In case we do not have any information about the user position, we can start with 0. And with some multiple iterations in the first time instant, using weighted least squares, EKF will not work. If we do not have any prior information, EKF will not work right away. We have to start with weighted least squares or simple least squares, but do multiple iterations, converge to some estimate, and that estimate can be used to start the extended Kalman filter. We cannot straight away go to the extended Kalman filter if we do not have any good guess. Okay. For the extended Kalman filter, we also need a process noise model that accounts for the inaccuracy in the state propagation. For example, here we have not modeled acceleration, but the user can have some acceleration. That inaccuracy can be addressed with the help of this process noise. And then based on the knowledge of user motion, its covariance has to be set properly. Q has to be set properly. It is again modeled as Gaussian with zero mean and covariance Q. Q has to be modeled properly based on the knowledge of user motion. What kind of user trajectory we will have? If it is an aircraft, what kind of path it will fly? So based on that prior information, Q has to be set accordingly. Here I have just given the equations for the Kalman filter time update and measurement update equations. I'll not go into this again because we already discussed this in the class. Here we did not estimate the user acceleration, but it is also possible to estimate the user acceleration. Okay. Now we have considered the user position and velocity with respect to the ECF coordinate frame. It is also possible to have a formulation in the local navigation frame. When we do this in the local navigation frame, we need to consider latitude, longitude, and height above the WGS 84 ellipsoid. In that case, both the state transition and measurement models will be nonlinear. In this case, it is linear. A is a linear matrix. It is just a function of the time interval t. But if we have the formulation in the local navigation frame using the latitude, longitude, and height, then A also becomes a nonlinear matrix. Both A and H would be nonlinear there. Okay. So the implementation is more complex, but it is possible. What is the accuracy that you can expect with pseudo-range and pseudo-range rate measurements? Meter level accuracy. Horizontal positioning accuracy is typically 1 to 2 meters in good signal environments, and vertical accuracy is on the order of 5 meters. Why the vertical positioning accuracy is worse than the horizontal positioning accuracy? This is because of the geometry of the satellites. Now, if you consider the horizontal position, you will see satellites all around. Some will be in east, some will be in north, some will be in northeast, southeast. So they will be spread all around in the horizontal direction. But how about the vertical? All satellites will have to be on top. Generally, by design, the antenna will not receive signals that come from below because they are more likely to be multipath. So satellites which are on top, signals which are coming from top are given more importance. So it is not possible in case of the vertical position, some satellites are on top, some satellites are below, some satellites on the horizon. We do not do that. We generally consider satellites which are on top. Since we do not have even distribution all around in the vertical direction, the vertical accuracy is worse than the horizontal accuracy. Can't we get better accuracy? Yes, of course. If we use the accumulated delta range measurement, the carrier phase measurements, we can get sub-meter to even centimeter level accuracy. But as we discussed, it is easy to lose log of the carrier phase tracking. If C over N naught is not good, or if the user motion is changing fast, then it is easy to lose track of the carrier phase. Then we will not have accumulated delta range. We can somewhat address this problem by providing some aiding, external aiding. Then the tracking loop can better handle the dynamics part. Of course, then the performance improves. If we can provide some aiding, say INS aiding, then of course we will be able to better handle dynamics even with the carrier piece. So this completes the discussion. We have 4 minutes left. If you have any specific question, you can ask. Otherwise, you can leave. The exam, the class test will be on 7th April from 8 to 9:30 am. It will be held online. And I have already told you the syllabus. I'll send you the instructions in a separate email shortly. Syllabus is from estimators till today's class. Whatever we discussed under GNSS and estimators, everything is included in the syllabus. That's it. You can leave now. If you do not have any question, you can leave.